My name is Bill Schindel. I'm with ICTT System Sciences and share the INCOSE working group called the Patterns Working Group, or the MBSE Patterns Working Group. This lightning talk is about a series of 3 questions that we think in our working group need to be asked more often, and because they lead to some important insights. And so we try to do that. And it turns out these are questions that have been dealt with in the past as well by our forebears, sometimes a century or more ago, with great power, but sometimes we forget to ask them. So as we go through this briefly, we're going to think of it as opening 3 doors. There's 3 questions, and each time, if we have the courage to open the next door, we get some new insights, and it changes our way of thinking about things. At least that's the idea. The first question is, what's the simplest model of a system? We're really asking ourselves, for purposes of engineering and science, we have to add that particular point. What's the simplest model we could represent that would satisfy our purposes as engineers and scientists over the life cycle of a system? It turns out that people have dealt with this a lot in the past for practical reasons and for kind of theoretical reasons. It's practically important to us because we know that as system engineers, we're famous for producing mounds and mounds of data. Sometimes we just have more than we want to make use of. And so the question is, what's the minimal amount we would need to do a good job over the life cycle of a system? As well as the idea that we might be missing some. Smallest means not too small. So how do we know what the smallest amount that's still sufficient would be? Of more maybe theoretical interest for those interested in complexity and the like is that one of the mathematical definitions of the complexity of a system is the length of the shortest description of it. So if you're into that sort of thing, it's also a kind of important theoretical idea. And in science, there's a great history of Occam's razor, the idea that often truth lies in the simplest explanation of something. So that's why we see Copernicus and eventually Newton there. They were rather famous for the idea of finding the simplest representation of the strange motion of the stars and planets, which turned out to be the Earth was not in the center of the solar system, unlike some of the more complex explanations of why things move the way they do. So seeking that smallest model has led us to some surprising conclusions. So the way we start out in this, thinking about it as engineers, or maybe scientists, technically trained people, is that by system, we mean, at least in this context, we mean a collection of interacting components. And by interacting, we mean the exchange of energy or force or material or information that drives the components that are interacting into different states. And by state, we mean an attribute of a component that causes it to behave differently during those interactions. So it's kind of a circular idea, and reminds us that, as far as we know in the physical sciences, there is no behavior, no model of behavior, no behavior at all that's not in the context of interactions. There's no naked behavior in nature. The only behaviors we ever see are during interactions, and all the physical laws are written about interactions. So it's pretty important over the history of that time. And this is kind of the attitude that Newton had after he sort of worked out the nature of, he might not have used exactly the same terms, but this was sort of an important paradigm about what we mean by system, even though other people, maybe not in this room, have other definitions of system different than this. This is one that we use. And so as system engineers, we get faced sometimes with maybe in a argument in a bar, let's say, for example, with other engineers that are mechanical engineers or electrical engineers, with the idea that we don't have real phenomena the way that the other disciplines do, with real physical phenomenological aspects and real mathematics behind them and so on, and that system engineers instead are organizing information in a clear way and coherent way and coordinating across the different disciplines to have a good result, and all the other things that about 1950 our system engineering forefathers organized system engineering for. And so when we go to point to our system equations and system phenomena, at least the popular attitude is, well, that's not exactly what we do. So we're hard-pressed to present ourselves as being based on a hard science. At least that's one point of view about this. So the system phenomena says otherwise. It says when we take that attitude of what we meant by system about interactions, we encounter this idea that behavior that emerges from the interaction of the behaviors of the interacting things a decomposition level lower, is what makes a system behave the way it behaves. And specifically, that got worked out by lots of our progenitors, especially by William Rowan Hamilton, who presented us with Hamilton's principle. That's a mathematical construct that happens to describe the trajectories that a system of any sort that's having those interactions will take. And in case that seems like pretty abstract stuff, it happens to be the basis of all the physical laws of Newton's laws or chemical behaviors, Mendeleev's organization of the elements, Maxwell's equations, even quantum mechanics, are all textbook derived from Hamilton's principle. So it's got lots and lots of 150 years of exercise behind it to show that it's been very, very important to us over a long time. And the equations that result from that might not be solvable symbolically, but most of the equations we deal with these days are not. They can be simulated and often are by engineers. So this would say, actually, there is a phenomena, a very abstract general one, but it's quite tangible, and it has mathematics to go with it. It's a real phenomena. Moreover, because all the physical laws of the other disciplines can be derived from Hamilton's principle, it turns out that it's the base phenomena that all the other disciplines depend on. So it turns out that it's not the system engineers that are without a phenomena. We provide the base phenomena that all the other disciplines claim to have their own unique phenomena that are really derived from it. So that at least should win the bar argument for you. More seriously, this kind of leads to the idea of thinking about where we are as system engineers in a much different way, because the traditional view of systems engineering, at least that I was taught, most of us are, I think, on the left side, is that there are underlying physical phenomena, chemistry, mechanics, and so forth, electrical science, and from those arise the traditional engineering specialties of electrical engineering and so on. And then as system engineers, we come in at the top and make it all sort of work together at the so-called system level. Well, that's the traditional view, but once you soak up this other answer that we're talking about here from this question, you realize that actually the system phenomena is below all these different disciplines. And from it are derived the systems engineering discipline that we talk about as kind of an abstract discipline at that level. And from those come the traditional disciplines, and then most practically and important, above those are higher level disciplines that some of you practice that have to do with vehicular patterns, aircraft patterns or otherwise. There's lots of those that have come out in the last 25 or 50 years. And then there are more above that we expect to become disciplines as we understand the patterns of those higher level systems as well. And so this is a very practical kind of idea that says this is where we get our future disciplines and ideas from, and it's all systems engineering, not the conventional view. So when we model this as modelers, we use an underlying meta model, especially it's called the S meta model in the patterns working group, and especially features this idea of interactions as the heart of the whole thing, as we just described. And so we call those models S models. They can be expressed in SysML or whatever your favorite tool is. It's not about a modeling tool, really. It's about the underlying ideas we express in it. And that's what our patterns working group makes use of. The second question, and the door that goes with it, is about the idea of, do we have to keep repeating other people's learning and mistakes? And I think you all have your own stories about how that goes. Part of our problem here is that we have this very good set of definitions of how we should do our work in system engineering. The INCOSE handbook and our company's descriptions that are highly proceduralized. And actually, they're pretty good in the sense that they're a guide to all the things you might need to do your work. And so the question might be, what if I already know a lot of things? Because they show us everything we'd have to do if we didn't know anything about the domain we're working in. And that doesn't mean you have to, by rote, do them all. But the answer to what would you do with what you already know is kind of ad hoc. We haven't really formalized that very much. And this is the idea of patterns, is to begin to formalize how do you mix information together and what's the theory of that mixing, so that we can really be sure we take advantage of what we know and also deal with the idea of who's we. Doesn't mean what do you know where your colleague down the street or next year didn't know that. It's what do we collectively know. It's what patterns are about. Those patterns are recurrences that have fixed and variable parts. They're the heart of the physical sciences for the last 300 years. They're all based on patterns, and we're just expressing that very idea and trying to emulate what science has already taught us. Hamilton's principle and Noether's theorem are very much about those and provide lots of good mathematical and theoretical and solid basis for them. So this is not kind of an ad hoc, informal idea at all. So these patterns that we're building out of S models are called S patterns, which simply means that they all conform to the same underlying meta model, and it guarantees us that we're going to express ideas like interactions, emergent properties, and attribute couplings, and value, and the notions that apply to represent the general idea of being a vehicle versus the specific configuration of that pattern for a certain kind of vehicle, like a cement mixer, for example. The payoff of this is that we can do things very fast compared to what we're used to. That's one kind of payoff. And it's like an order of magnitude improvement in that sense. But also that we can start out with very, maybe not finished, but very relatively complete descriptions of the systems we're trying to do. Not to say that we believe them, because we always have to hand adjust them, but we have fantastically good first drafts by doing things this way. This all runs into cultural challenges, because we all, like all of us in INCOSE that do models, like to make our own models and model from scratch. And as our earlier speaker mentioned, that's not necessarily the optimal way to do this. And likewise, we don't want to all create our own private ontologies or our own private patterns. This isn't really powerful until you share them. So the question is, how do you do that? And Thomas Kuhn very famously wrote on this and what happens when paradigms shift and groups aren't sharing those paradigms. There's all kinds of interesting human literature about this. And so this turns out to be the hard part, is how do we shift gears to an environment where we do that. So we use some models in INCOSE called the System of Innovation pattern that describes for any innovation project of any kind whatsoever, performed badly or well or otherwise by any method, what's the general reference model that represents learning and group learning. And this pattern, this particular pattern, the System of Innovation pattern, is used for that. And it's detailed in a lot of the publications out of the group. The third question and door is about, it's the most current question, is about reconceptualizing systems engineering. Simon Ramo and his other very smart colleagues back in the mid-20th century, in the 1950s or so, brought us the early versions of our formal practice of system engineering in order to organize what wasn't going so well at the time. We were building systems too complex to make them work, and so we began at that point to be more formal about the idea of what we think of system engineering until fairly recently. The question is, what's the future of that going to look like, which is something that we're wrestling with in INCOSE. And so this door is about how would you reconceptualize system engineering to consider what the first two questions told us. When we thought about the use of smallest possible models, we thought about the idea that we're using patterns that we learn collectively and we don't have to relearn individually. Doesn't that affect the way we perform system engineering? And of course the answer is yes, very much. And that brings up all sorts of interesting questions that we're wrestling with in INCOSE right now. And so one of the most important patterns to talk about is the pattern of doing engineering, or more largely, the pattern of doing life cycle management of systems, which includes their early concepts and fielding and manufacture and distribution, sustainment, and otherwise. And what does that transform process look like? And the slide here hints at the answer, in that the earlier answer to this was to think about the V diagram, or whatever your favorite representation was, of all the process areas we have to carry out procedurally. And there's a long-term emphasis, last 50 years, 100 years, on the procedures of systems engineering, where we also, to some extent, refer to what the information is that's passing through those procedures, but it's not the main point. And so we emphasize the process on the left side. The right side represents the future vision of a transformed process that says, yes, we'll still have procedures, but you don't often talk about the procedure of doing electrical engineering or the procedure of doing chemical engineering, even though there might be a few. More likely, you would talk about the equations of motion that are brought to us by Maxwell's equation, or the reality of Newton's laws, or we'd think about the chemistry, the underlying chemistries. That's a lot different than thinking about procedure. That's about the representations of the engineered system of interest. And so this transformation, whatever it may be, we think is much heavier on the representation of the underlying thing that we're engineering. And so that's why modeling makes this also important, is that modeling is how our last 300 years of engineering and science progress really happened. And we're catching up with that now as system engineers, which would make us think that there'll be a shift in dominance. You might still have some procedures, but will be much more heavily dependent on what is the information telling us about those procedures. A little hint at the insufficiency of being procedure-oriented is that all the procedures we have now tend to say at the end, if everything isn't right yet, do it again. They're all iterative. And so even though they might look like sort of sequential, in fact, they're not sequential. They're trying to drive us through not procedure space, but system configuration space. So that means, am I done, isn't a question about what procedures have I followed. It's about what's the status of the configuration information describing the system, which is a shift in the mental way we look at this stuff. As you do more of this, you get more and more thinking about the dynamics of the configured system in configuration space, because now with models we can really talk about ideas like configuration space. It might be the configuration space of fitness, or the configuration space of faults or requirements or physical architecture or otherwise. They're all part of this, but it more and more starts to look like the idea of agility and configuration space in the sense of control systems. And so there's whole theories about how to drive optimally through different configurations that we've used very successfully for the last 50 years or so to think about flying and other sorts of optimal control and estimation that become available when you shift your attention quite a lot, not to procedure, but to the status of the modeled system. So we think more and more about this kind of dynamics as we're going through loops that are learning and execution loops, where we're much more than in the past emphasizing the idea of learning, discovery along the way, and separating off the idea that we know a whole bunch of stuff from the past, and we've done lots to make it credible, gone through all sorts of processes to make it credible. We want to use that as well in what we execute. It also makes us think of pattern data as intellectual property, where we can actually think of information as capital. It's actually, under the Financial Accounting Standards Board, possible to capitalize financially patterns and treat them as a new way to modify the economic curves that we're all taught in INCOSE that says front-end engineering investment in system engineering reduces the later expenditures and problems, which it does. But what if we were to use that front-end expenditure not in the form of expense, discovering things again, but in the form of using capitalized intellectual property that's already in our patterns, another way to gain that knowledge at the front. And it's a different mindset when you start thinking about balance sheet views of information. So the question is, about reconceptualizing system engineering we come to at the end here is, would you like to step through door number 3 with us and help answer this question? First door we went through was, what's the smallest model of a system? Which pretty dramatically changes our way of thinking about what we can know and what we must know about systems. The second is, how do we avoid learning over and over and making the same mistakes over and over as a society or as an enterprise or as a team? And that's through the use of patterns that more effectively are melded into the engineering process as muscle memory. And the last is reconceptualizing system engineering. So I hope you'll join us in the Patterns Working Group to be part of this. Thank you.